Thing?
You got it. Now, what I want to put in capital letters is this phrase, at least one. At least one. At least one. What's the problem with it? At least one. And then they said is right-handed. Okay. It's like even though it's in the book, I like to write this stuff out so you can see what's important, what are the keywords. The last one didn't have many keywords, but we put in our own words, we knew it was and. This idea of both. When you hear this phrase, at least one, get prepared to use, what rule is that again, Art?
Complement.
The complement rule. Get ready, what we're going to do is we're going to take 100% and subtract a probability. Because what we're looking at here, at least one is right-handed. And when that means this person's righty, right? Or, oh, here comes the or
This one.
that person's the righty. Or, there's another sscenario, they're both what?
Righty.
Righties. Well, that seems like the long way to work this problem, don't you agree? Because or means we've got to add probabilities, true?
Mm-hmm.
So it's like, man, that's gonna take I gotta do the probability that this one's the righty. Add it to the probability that this one's the righty. Or plus one more, add the probability that they're both righties, right? Well, all probability, the probability of all events occurring have to add up to 100%, right? Which is 1.0. To quickly do this, it's the complement rule. We're just gonna go, here's the answer. It's 1.0, 100%, minus the probability that they're both lefties. All right? Excuse me, both,
Righty.
right? At least one is right-handed. That means 100% minus probability, excuse me, both lefties. Sorry about that. We'll do this over and over and over today. Don't let this phrase, at least one, ever scare you, intimidate you. We'll use the complement rule. I'll go 1.0 minus the probability. And you know what's neat? See this part A, part B? It's usually set up like this, which is helpful. I'm just going to subtract out my last answer. Because what was the answer to my last question? What was the probability that they were? Both lefties, which was which number?
This
Right there. This is going to give us the answer. If everything's got to add up to 100%, all possible, right? Possible events occurring right and left, or left and right, or right and right, or left and left, everything's got to add up to 1.0. The odds at least one of them's right-handed, which is like, well, that means they're not both lefties, right?
huh.
Do you agree? That means they're not both lefties, so 100% minus that. And this should be a very high answer because we get 1.0 minus 0.0169, which gives us,
0.9831.
thank you. There's a really, really good chance of this happening.
I got one question.
Really good chance, Art.
It's between two people, right? So
Yeah.
one will be left-handed, one will be the right-handed, right? So why are you taking the probably both of them lefties then? Shouldn't you take one as a righty, then shouldn't you separate like 0.13?
Yeah, I'll write out all the possibilities. Let's write them out.
Okay.
Almost like this is our sample space. That's what they call it. Like, what are all possibilities right now, everyone? Let's use L
And
for the lefty and R for the righty. And
okay.
there's two people, right? Let's look at all possible scenarios. What's one of them?
LL,
Yeah, they're both lefties. What's another one?
LR,
LR. First person, second person. Give me another one.
RL,
And there's one more.
RR.
And what we did was, we just took 100%. Ready?
Uh-huh.
100% subtract that, and it gave us all these.
Okay.
Isn't that cool? Feel free to write this in your notes. We're taking 1.0 minus the probability of that event. Gives us all these possibilities, which is really high. Isn't that cool? It's called the complement rule. You go, you can always use it if you hear this phrase, at least one. Now, if you're curious about at least two and at least three as we go on, I like your curiosity. We'll get to that in chapter 6. So don't worry about that today. What? At least two or three? Like if you got 10 lefties, you want to know what's probably at least 5 lefties. That's for the remainder of this course, which is cool as well. Everyone, great job at that. Okay, this is number 17 on page 285. Where's that? A lot of you are like, yeah, but you put 17 as one of our practice problems. Every once in a while, I like to do a problem that's actually in your practice list. We'll extend it though. We'll extend it. After I do 17, I'll make up another one. All right. First of all, this is about 40-year-old males. And the probability that 40-year-old male lives another year. Randomly selected. So P stands for probability. The probability that a 40-year-old male lives to be 41 years old. And when they have the statistics on this from the National Vital Statistics Report, right? Do you think it's high?
Yep.
You think it's pretty good? Yeah, it is. It's pretty darn good. 1.99. This is for a randomly selected 40-year-old male, 757. I mean, that's really good. Hey, when number 18 is about a randomly selected 40-year-old female, that's higher. 0.998. Better chance, right? Hey, do you think it was this high 100 years ago? No. Very good. Do you think it's this high in some other countries? Very good. Very good. That's really good. I mean, you're statistically literate. That's really cool. So that was given to us. Well, what's letter A ask? All right, letter A. What is the probability that 2 randomly selected 40-year-old males live to be 41? What is the probability that 2 randomly selected 40-year-old males live to be 41? All right. Live to be 41. They live another year. I'm thinking, is this or is this and? All right, here they are. They're randomly selected. They're both 40. What's probably you make it another year and you make it another year. We're multiplying these, right? And they're randomly selected, so definitely independent events because they're just randomly selected 40-year-old males, right? I didn't go to what? The you know, this would sound terrible, but the club of, you know, people are being treated for cancer. You know, it sounds odd, but you'd be like, wait a minute, I don't know if that would be actually 0.99757 or something. So we're saying randomly selected. All right, 0.99757 times 0.99757. Or what's another way to type that?
Square.
Square. Some of you may want to do 0.99757 squared. I bet you this is still around 0.99, isn't
Yep.
it? So I'm going to write it out to a few places. What do you get? 99.
514.
See that? Stays pretty high. All right. You know, now on B, I want to go, what about 5? What's the probability that 5 randomly selected 40-year-old males? 5. Randomly selected. So they're all randomly selected. I won't write that. 5 40-year-old males. 5 40-year-olds live to be 41. Okay, this time, everyone, I think I'll write it the fast way. 0.99757 raised to the 5th power, right? Caret 5, raised to the 5th power. It's probably still really high, but I'll go out to the 3 places again.
0.9879.
9879, I think I'll go to 3 places here.
988.
Right, or Autumn will do the 3 places. Yep, oh good. She's like, cool. 988. And I didn't see the at least one yet, did you? Me either. Alright, here it comes. And what's the probability that at least one? At least one. Now, they gotta be clear here. They talking about the 5 people or the 2 randomly selected? They said a 5. So probably at least one of 5 randomly selected people who are 40 years old. So 5 randomly selected 40-year-old males. These are all males. 40-year-old. What's the probability at least one of 5 randomly selected 40-year-old males? Everyone, the author wrote this. Does not live to be 41. Can I make that brief? I think they're using euphemisms here. Can I just say the word does? Right? That's what they're saying, right? At least one of 5 randomly selected 40-year-olds does. That's what we're hitting there. Does not live, they wrote. So, everyone agree a complement rule?
Mm-hmm.
We'd at least 1.0 minus all 5 live.
Mm-hmm.
And I think we have that somewhere on the board. All 5 live. 1.0 minus probably all 5 live. And you look back to your previous answer. Be careful though. It's not that number. That wasn't for 5, that was only for 1. So all 5 living was the,
90.
see it right there? So I'll even circle this and bring it down here. I'm gonna go, you're coming, sneak through here, right there. And it's a 1.0 minus this 0.012, which gives me roughly, it's gonna be pretty high. 0.9, is that 88?
Mm-hmm.
There's the odds.
It's backwards.
Oh, 1 minus the,
Yeah.
Point-
0.9.
what is that gonna be?
0.12.
0.12?
Yeah.
Oh, thank you so much. I was looking, going, what am I doing? 0.988. 0.012. So 1 minus 0.988, giving us a very small chance. This would be unusual, wouldn't it?
Mm-hmm.
It's unusual. So 5 randomly selected people, and there they are, and they all met one day. And they're just like, yeah, think we'll make it one more year? Well, the chances that they don't are very small. Right? Very good chance you're all gonna live another year. True? Hey, I wanted to extend this, because I didn't want you to think this was always very small. So how about this? I'll erase letter A, I'll erase letter B. Actually, I'll leave B up. I'm thinking of like a high school reunion. And that's what I'm thinking of right now. How about a high school reunion? All male school, somewhere like the Matha, right? And let's just say there's 600 males in the senior class. So what I'm saying is, here's this reunion. What's the probability that 600 40-year-old randomly selected males live to be 41? Well, is that going to be as high?
You can try it.
Right? Let's see. That'd be 0.99757 raised to the,
600. So 0.23.
so it comes up?
Yep. Yeah.
What was after the 2?
2322.
2322. So what's the probability that at least one of those 600? See, sometimes this will happen. People are in discussion, you're like, did you hear about Fred? You're like, yeah, that's so sad. You know, Fred passed away and stuff. But it is shocking to people. But I want you to see, when you're talking about 600 males, 600 randomly selected males, the probability at least one of the 600 randomly selected 40-year males dies, this is not unusual.
77.
Because you take 1 minus the what?
0.23.
2, 3.
0.77.
We're saying, well, there's actually a pretty decent chance that that will happen. You follow me? Welcome to probability. It's very interesting sometimes. We kept looking at 2, and then we looked at 5. We're like, well, what about 600? Right? Some gigantic reunion of 40-year-olds. That's like, well, there's a decent chance that one of them may not make it that next year.
When they do the quality assurance, like yeah, when a light bulb will fail and all, do they use this kind of thing?
Yeah, exactly.
Uh,
Exactly. And if you ever want to do at least 2, or at least, because it only takes 1 to knock the whole thing out, right?
Yeah.
So they use this. And the one about the light bulb, where is that? Number 16 has the Christmas lights. If anybody wanted to try it. Cool. Number 16 has the Christmas lights. String of 100 lights. Da 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 da. And they get letter B. What is the probability that at least 1 bulb will burn out in 2 years? Has that ever happened to someone? The 1 bulb will what? Yeah. Hey, well, great job with this. Love this stuff. Before we even get to that 5.4, I still want to do one more. It won't take that long. And when it's still on page 285, this is titled Cold Streaks. I just thought some of you might have a question on number 23. That's the reason I'm doing this one as well. I didn't want you to go back and go, all right, I got his problems in class, but I'm not understanding 23. There's something funny about it. And we're talking about players in cold streaks, and they're talking about a hitter who successfully reaches base 30% of the time. Any baseball fans in here? They call him a 300 hitter, right? They're saying his batting average is 300, but they're talking about that. In baseball, they like to go out 3 places past that decimal point. So there's that base. That's a good hitter. But I'll just chop that off. Same number. That individual, he gets on base, all right, 30% of the time, successfully. Reaches a base. Maybe first base, second base, home run. All right, 30%. So that's the probability that that player gets a hit. Gets on base. So far, so good? Now, they didn't ask this, but I wanted to throw it out to the class.